I'm Roozbahani from Group 15, and I have with me in this group James Matthew, Hira Anis, Bilal Mufti, and Shakir Shakur. The topic of our project is handling the curse of dimensionality through random lasso regression. In real-world scenarios, especially in the field of bioinformatics and genomics, we frequently encounter datasets with a lot more features than samples, such that the ratio of features to data points is in the order of 500. Such is the data on which traditional model fails and leads to research constraints. This problem will be analyzed in our project. The dataset chosen for our analysis is gene expression data for breast cancer, which has 6 classes, 151 samples, and expression data for 54,676 genes, also known as features. In our project, we will first perform principal component analysis on this dataset to reduce the number of features, and then we will observe how this PC-applied dataset performs under supervised learning algorithms such as regression. We will then switch gears completely to supervised learning and will entirely use regression analysis for feature reduction as well as prediction of labels. In order to apply PCA, which is an unsupervised learning algorithm, the labels were removed from the original dataset and then PCA was carried out using scikit library of Python. PCA basically helps in dimensionality reduction by orthogonally projecting the data onto lower dimension linear space while maximizing the variance of projected data and minimizing the mean squared distance between projection and data points. The application of PCA on the discussed dataset with the retention of 99% variance resulted in intrinsic dimension of 143, which represents that we need 143 features to reconstruct our data with 99% variance as shown in the plot between cumulative variance and components. Here is the visualization of transformed dataset with 2 or 3 principal components through 2D and 3D scatter plots respectively. It can be seen that even 2 or 3 components are able to capture enough variance and data can be meaningfully visualized. Next, we applied regression on dimensionally reduced dataset. Since regression is a supervised learning technique, it was required to split the data into training and testing sets. However, it is not possible to use categorical data directly for regression, and hence label encoding was used to assign numeric values to the labels. When splitting was done using 80-20 division rule such that the training data contains the first 80% of the labels, the RMSE values obtained were pretty high, and on analysis it was revealed that data on which the testing was done had labels on which data was not actually trained. It was then realized that for datasets which are more sequential, this can be an error-prone technique. To overcome this issue, the data was split randomly. 3 different regression techniques including linear ridge and lasso were applied, and expectedly RMSE reduced from linear to lasso as shown here. 10-fold cross-validation was applied on ridge and lasso regression to find the most optimal lambda as shown here in this graph for ridge regression. Leave one out cross-validation was also tested but demonstrated poorer results comparatively. Overall, it was established that PCA is not the most suitable dimensionality reduction technique when it comes to datasets like ours, as we will observe later, comparing it with supervised part which shows better results.
Supervised learning, we're going to be looking at the dependent variable y as well to try to tackle this problem of high dimensional data. Intuitively, I like to think of the samples as being the actual data, whereas the features is something that we have to predict, to ultimately predict y. So it's quite burdensome actually to have a lot of features because that's just something we have to solve for. So that's not really having more data at all to have features. For dimension reduction, we try to use PCA, which doesn't look at the response variable y, and PCA will treat these features with high variance as important, and where it can be such the case that these high variance features have nothing to do with the response variable y at all. We look at a palette of regression techniques here. What's most important is the lasso and elastic net regression techniques reduce many of these coefficients to 0, which is quite exciting because then we can reduce our features to a handful of important features, whereas we're not so much caring about the actual coefficient values anymore. We just want to know which features are important. And we see that lasso, in terms of RMSE, when we throw all these regression methods at the problem, lasso will perform the best. And the mean guess RMSE is quite an important benchmark because the mean guess RMSE, if your RMSE is worse than that, then your regression technique is performing no better than just a toddler guessing. So we have some promising results here to find some meaning from the data because a lot of these RMSEs are lower than the mean guess. So lasso reduced the important features down to 250, elastic net 195, and we also look for agreement in all these regression methods. These are the indexes of the most important pronounced coefficients in the negative or positive direction. There's a lot of agreement. These are the indices, okay? And so there's a lot of agreement among all the regression methods, so we're pretty happy, and we think we're finding something good here. If we plot all these out, this is actually plotted in quite an intuitive way if you later read the Legion down here, where you can look for certain alignments between all these regression techniques to find areas of interest. Like this cluster over here is quite interesting, these genes over here. seem quite important to us. A lot of the regression techniques are kind of in agreement on its importance. Next, we try to tune elastic net, and you can tune it more than just the lambda value. You can also tune it in the ridge or a lasso direction. And if we tune this, we can actually get the RMSE all the way down to 0.5. That's a lot better than even lasso did. There's this kind of ridge of prosperity right here, where elastic net's RMSE decreases drastically, and this perhaps is calibrated to the exact amount of features that's correct. And this is a further zoom in on that elastic net tuning that we did, where we found the ratio of lasso to ridge to use there. And this highly tuned elastic net had great results, a very low RMSE, insane, and reduced the data set down to 300 features of importance. And we also plotted that as well. And actually, I played a little trick on you, because the RMSEs I showed you earlier were not the five-fold cross-validated ones. Those were just tuned with five-fold cross-validation. When we look at the actual RMSE with five-fold cross-validation, they're all quite horrible and even worse than a toddler's guess. And so what I said earlier about features being this high, it's impossible to predict these coefficients with such a high amount of features. And so that researchers never have to go through this problem again, I simulate a bunch of data where we look at the ratio of features, samples, and important features, or non-zero coefficient features. So I have a new theory that it is not so much the case that features being greater than samples is an issue, but I think perhaps it's more so the case that important features or non-zero coefficient features being greater than samples is the issue. And we analyze this through all these regression techniques down here, which give researchers some intuition on which one's best to use in certain situations and certain data sets. We create a robust set of functions to simulate hundreds of and thousands of simulated data sets of different shapes and dimensionalities to try to find meaning in what regression techniques perform the best. So we can look at that later. But random lasso, we tried to implement that in Python, but it's quite challenging. But we do know that random lasso shows a lot of promise in outperforming all the other regression methods in RMSE when tuned to in a certain way and with certain sets of data. So we want to look at that more, and that's a question we have still